Okay. So yeah, as I said before, I'm hammering you pretty hard at the moment. And again, I'm trying to make up for past mistakes where I sort of didn't go into the fundamentals long enough, and students were lured into thinking, this is easy, and then it became impossible when we got to the control and later on. So I'm giving, for the first time, I'm finally doing what I always promised myself I'll do, and that's giving you homework every week, just so I can see, understand what you all know, and also to make sure you get going. I'm going to do it to you one more time. So the next homework assignment will be due next week, and then I'll let up, okay? Because we'll have covered really the tough stuff. Let's see. So you saw that I uploaded two terrifying, to some of you, part of it to all of you, handouts. Lecture Note 0 is mainly a review of just the basic measure theory you learn in noise, or reviewed in stochastic methods too. But the other lecture notes 2, is like a 36-page compression of my book with Tweety, in the special case of countable state space Markov chains. So I'm only giving this to you as a reference. I'm not expecting you to know all this stuff. So I'm going to go through maybe 5 pages of this, but it's a short course on the topic. So, all right, so you all understood, right? All right, so I need those pens. Are they still in there, I hope? Did somebody take them out? Oh, Jesus. No, they could have been taken out. Who would take them out? They're in one of those pouches.
Oh, yeah.
Yeah. Okay. So I'm going to start off, in hour 1. I want to go through those lecture notes 0, and at least the first half in hour 1, which is just omega FP. Now let me just start with the motivation. So if you take a baby probability course, and suppose you want to say, what's the probability that Y is motivation? You ask this question, all of you would say, oh, that's easy. It's the integral from a to b of f sub y of y dy. Problem solved. Somebody gives you a density, and you integrate it from a to b, there's a probability, right? And so maybe it's a Gaussian density. All right. All right, now what if I ask you a question, what's the probability that 1 over n, sum k equals 1 to n, that's a capital, of c of xk, so this is my Markov chain, and c is a cost function, what's the probability that goes to some constant eta as n goes to infinity? All right, there's our A. Where's the density? How do you make sense of this? So there's nothing in an undergraduate probability course that lets you even talk about this. It's meaningless, right? You would have to have, this thing has to have, there has to be a density associated with it or something. It doesn't make any sense, right? And so that's why this abstract notion of probability spaces comes about. This omega FP, which is all Kolmogorov's craziness. Is used to answer questions like this, to set it up so we can have a common language, and I can write this down and you all know what I mean. And so for those of you who want a job, at DeepMind or something, this is a common language there. I know people, at Google. Every one of them speaks this language. So it's not me trying to push a mathematical agenda. This really is a common language, okay? So not knowing handout 0 is a big mistake if you want to go into sort of AI world, okay? Unless you just want to code algorithms that are known and not, not go in deeper. In order to understand what's going on, does this algorithm converge or not, and how fast? Because we also want to know how fast. So this is going to end up being something like an algorithm. It's not going to be just an average. I've got some algorithm. I want to know, does it converge where I want to, and how fast? You need that guy up there. All right. So here it goes. And red is no good. So what's this about? So I got some practice yesterday because we ended up getting into this during these second office hours. I ended up giving today's lecture in about 20 minutes. So Kolmogorov's approach, which is the approach to probability, it's the only approach there is for stochastic processes, is that this capital omega represents the entire world. And so I was joking yesterday. So I don't want to say God or Allah or whatever. I came up with dog. So the grand dog, 2 trillion years ago, let's put a star there. So omega is a big set of symbols, okay? Now, once, did I write 2 trillion, maybe it was 10 trillion, I'm not sure exactly, and I'm not sure if they call him dog, and I'm not sure if it's a boy or a girl, or if it's actually an animal, but pick that omega star, and that was it. That was it. So you're about to think something? If I knew omega star, I would know what that is. If I knew omega star, I'd know the stock market tomorrow. I would know what my day of death would be. I would know, everything. I mean, so there's nothing random about probability. Dog chose that omega star once, and all of you are functions of that omega star. So it's nonsense. It's a model. It's a model, but it's the most beautiful model for trying to come up with a model of information. Because our goal is to learn omega star, right? Don't you all want to know the future? If we knew that guy, then I would know the stock market tomorrow. I'd know everything. So that's it. So everything is about that. So then a random variable is a function of omega. X is just a mapping of a real valued random variable. Just means it's a mapping from omega to the real, if it's a real random variable. I mean, there's vector random variables, there's random variables that take, values and symbols. I mean, but let's just think about real random variables. Yep.
You're saying that omega star represents like all the information in the universe?
No, it represents everything that happens and will happen and everything.
Past and in the future.
Everything, yeah. Omega star. Well, I'll write it down in a second. All right. So I'll get to that. I'll answer your question in a moment. So a random variable is not random. It's a deterministic mapping that for a real valued random variable for any little omega, x of little omega is a real number. But my point is, what really happened was omega star. So x of omega star, that's reality. Your question you just asked, that was a function of omega star, because that's it. It doesn't happen once or twice or anything. It's just happened once 2 trillion years ago. Dog chose it, and it'll never change again. There's nothing random. It's just that we never get to see it, unfortunately, unless somebody can hack dog, which will be really cool. then you could know the future. So if you could hack this, if this was reality, you could hack the system, you'd find this and you'd know everything in the future and everything in the past. You wouldn't need a Wikipedia, because it would all be a function of omega star. All right, so then you'd like to be able to, you can infer things, right? Because we observe all these functions of omega, and every time we observe a random variable, we know something about omega, and we can get closer and closer to figure what omega star is. You know, so if I'm told that if I find that you know, if I observe this x, right? Well, that's reality, and so I know that omega star is in the set of all omega such that x of omega equals 2. All right? And I'm going to observe a whole bunch of random variables, and every time I do it, I'm going to have another cut. I can get intersections and intersections and intersections. So I've got this giant omega here, and I observe a bunch of, I find that x0 equals 6, and x1 equals 24, and x 2 is equal to 1 or whatever. And every one of those implies a cut in omega space. I'll call that like S1, and this, or S0 I should say. So SK equals a set of omega such that xk of omega equals the number observed. Again, omega is just some abstract symbol in here, and my dream would be to learn that omega star, because then I know everything. And so again, I've got, when I observe 6, that's x0, little x0, then there's a set of omegas here, and there's an omega star there that I don't know. And then when I observe 24, I get another cut. And when I observe S2, I get another cut. And every one of these narrows down what omega can be, but I'll never learn it, because I would have to, wait forever. Yep.
You observe x of omega, you didn't observe the set S1.
No, I absolutely.
So
well,
you don't
no,
know
it's an abstract. No, I do. I mean, I don't know this function of omega. I'm just saying that I might not see these regions, but I am narrowing down what omega star is one by one.
Just, okay.
Yeah, that's all. I just want to. I want to make sure it's clear that the relationship between these probability spaces and all that in learning. Knowing omega star means we know the future, and so the better we can sort of estimate, omega star, the better we are at learning. Now that's a ridiculous goal, and that's why we narrow down our goals to something more realistic. Instead of trying to know the future forever, we try to get a good estimate of something in the future. Yeah.
Do we know the function x of omega exactly?
No, we don't. I'm just saying that I'm just trying to give an intuition about the fact that we're the set of possible omegas gets reduced and reduced and reduced as we observe more and more data. That's all. Seeing this is sort of, it's sort of meaningless in a way.
Shrinking our ignorance.
It's shrinking our ignorance, absolutely. As long as we're smart. Yeah. So naturally, we'd like to know the probability of these things. So, I'd like to know what is the probability of the set of omega such that x0 of omega equals this. So right now this is after 2 time steps. I've observed this. Right. Now let's go back before we've made the observations. What's the probability that this? Let's use different numbers. Just that this equals, 12 x1 of omega equals 64, and x2 of omega equals 8. Right. Now, if these guys had a joint density, it would be 0. Maybe we shouldn't be talking about equaling numbers. we'll look at that. So we have to be able to define that, all right? You know, so this is this I should put this in brackets. This whole thing is a subset of omega. Oh damn! You missed my whole poetry thing. All right. So when you're talking about probabilities, you're talking about the probability of all omega, such that something of interest occurred. All right. And the thing is that that is a subset of omega, and so this P had better be defined in all subsets of omega, right? And that's where you get stuck. You can't. So it's typically impossible to basically define P on simple, these are called events like this, and extend that to all subsets of omega. It's not possible, okay? And that is really advanced measure theory. I won't get into it, but there's no extension theorem. So we can't, okay, so you saw here, I looked at this set, this set, this set. That intersection, I'd like to know the probability of that, before I made the observations, and then from that, I'd like to look at any subset of omega. That's impossible, okay? So there's no extension theorem. And by that I mean, again, I'd have a model which would give me a formula for this. Like for a Markov chain, we have a transition kernel, we have a distribution for the initial condition, and so we can define probabilities like this for these simple sets. And then I'd like to extend to any subset, of my, any subset of omega, impossible, all right? And so what the trick was, the genius, is to define, so that fails. And so what you do is you define a domain of P. All right? So when you see that omega FP, I should have kept it up there. The omega, is easy to define. There's this thing we'd love to know. We'd like to predict the future. It just defines all these possible, everything is a function of omega. Omega star is reality. So omega is sort of easy to describe. P is easy to describe. We want to know probabilities of events like that. But F is a thing that scares people. But it's just the domain of P, and P is defined on subsets of omega. So F is a collection of sets. Right? Because I'm only looking at probabilities of subsets of omega. Yeah. Okay. Okay, cool. Okay, so, and then there's a bunch of things. I don't want you to memorize these things. I mean, there's some conditions that F has to satisfy. I can kill this. Oh, no. I guess I do have to say this. I mean, basically, the assumptions are kind of obvious. I'll go through it. Omega is in F. The empty set's in F. I want to be able to say, what's the probability of something happening? What's the probability nothing happens? Probability of omega is 1. you know, something happened. one dog pulled out some omega star. And of course, probably nothing happened to 0 as well. And you know, it's basically if you have a sequence, A1, A2, so forth. So you have a countable sequence of these sets, then that implies that the intersection, or I'll put the union, that's the usual thing. So these are minimal things you'd like to impose, because I want to know if I can define the probability of that, I can define the probability of a union. I'll need that, so you throw that in. And the same with intersections. So that was like 1, 2, and 3. Actually, 3 is just that if A is in omega, then the complement. I think that's all it is. If I missed something, I don't even care. It's not like this is a math course where I do everything. Mainly, I want to set down the motivation and the notation. You know, I'm not trying to review measure theory in 45 minutes. All right. So it's a bunch of axioms that are thrown in. I think I got them all. I'm not even going to check. I don't care. What, you think I missed one?
Third point should be A is in the set of F, not omega.
Oh God, that's why somebody's gasped. Yeah. I heard gasps. I wasn't sure why. Yeah. Yeah. All right.
The definition for probability equals 1 maybe should be P of F, not rather than.
No. So F is the domain of P. This is the thing. It can be confusing. F domain of P. So P is a function, some sets to numbers. So F is a collection. So A is an F means A is a subset of F.
Oh, okay.
Yeah. Okay. Yeah. And also this language. So when I say if A is an F, A is called an event. Now that's pretty abstract and bizarre until you look at this. I mean, you know, that's clearly an event. This happened. You know, the event is that I saw 12 at first, then 64, then 8, and it would say that's an event, something happened. You know, but that is a subset of omega. All right. Okay. Cool. And then lastly, the last definition involves that. Now, I claim I could get one of you who's never had a course in stochastic processes or measure theory or anything, based on what I've just said, you could give me the definition of a random variable. I want to know the probability that x had some value, right? So I'm going to have to be able to look at the probability of A, where A is derived from x. So somebody who's never taken stochastic processes, tell me what you think the definition of a random variable should be. Come on. Some brave CS student who hasn't had any background. You know, I don't want you to be right. Just take a wild guess. You know, remember, I want to look at I'm going to look at probabilities of A's where A is something about X. I want to know the probability that X is big or something. You know, X is like the stock market winnings tomorrow at noon. I want to know if it's big.
The probability of the random variable is smaller than something is even.
Well, what is a probability? That's a thing. That's the question. So I'll put it over here. so what you apply is I want to be able to say what's the probability that x is smaller than, say, 12. I want to make sense of that. How would I make sense of that? Now, I've already told you random variables, random variables are mappings from omega to the real line, you know? So I'm going to have to be able to define this in terms of omega, right? And so I'm going to have to like look at the set of omega such that x of omega is less than or equal to 12. And in fact, I'm going to give that a name. I'm going to call it, say, e sub 12. All right? So when you're asking, like, what's the probability x is small, you're asking, what's the probability of this set? And that set had better be in the domain of P. Okay? So it's a random variable if that set for not just 12 but anything. And sure, let's do that. All right. That's it. So that's a random variable. And so now you can see, now I can go through and go back to that original question. So, you know, there's our definition. And now when I write, what's the probability that 1 over n summation k equals 1 to n of, what did I say? C, oh, I use a c there. I'll use something else here. Yeah, you need some conditions. I shouldn't have put that g in there. Let's call it yk. I just realized that I have to be a little careful because xk could be a random variable, but you could mess it up with g. Well, I might shovel that into the rug as well. So if you have a sequence of random variables yk, you know, and I want to know what's the probability the average converges to some constant eta. Now that's a perfectly, we all have the same language. I'm asking, I've got a set A here. I'll call it A sub eta, where A sub eta is a set of all omega for which this is true. See what I mean? I got to my, you know, in 20 minutes, I got to the punchline. I want to be able to make sense of this question. You know, is this probability 1 or not? You know, and to make sense of it, I have to have this crazy dog up there, and because I have to have some way of making sense. This is the only way to make sense of it. You know. I was joking yesterday, I think fuzzy logic was invented because people were terrified of this. And I don't think it got us very far in terms of understanding the world. I don't know. I mean, some of you might want to differ, but so let's see. Now, fortunately, we don't have to be that abstract. Do I really want to do this? Yeah, I don't. I don't want to say much more. So, you know, there's ways, if you really feel insecure, there's a way to actually construct and make it explicitly for your problem of interest. But there's no reason to do that. You really don't need to. You know, it's just, this is really, in a way, just a mechanism so we can all speak the same language. You know, you know, people say in the beginning of these papers, let omega f p be a probability space. That's code for saying, hey, when I write this down, you all know what we mean. That's really it. I mean, wouldn't you agree? I mean, yeah, I don't know. You know, because you have to make sure people know what you mean by something like this. You know? And there's only one way that I know of to make sense of it, and that's it. Okay, so there's more here about that construction. What I want to do is just jump straight to Markov chains, you know, just because I don't think it's helpful. You know, I think that this is the punchline I wanted to get to. So, I guess. No, I do need it. I just don't, I'm so afraid of burdening you with a bunch of definitions that you don't necessarily need. But here, it is useful. I take it back. These notes will be needed. So kill this. Yeah. Okay, so I defined a real valued random variable here. To simplify things, I'm going to go a little further, but to simplify things, I'm going to stick to countable state space Markov chains. So so xk is going to be a random variable. Now, x might be a bunch of symbols, you know. It might be the alphabet. It might take values of A, B, C, D, E, F, G. And so this isn't going to do. But it's easier in this case, you know. So each xk is a random variable. And you usually write RV, you know, for random variable. It just means that I can make it easier. I can use like E sub x, or comma k. You know, when you have a countable state space, you know, when random variables take on, you know, instead of, you know, real's harder because there's so many possibilities. If it's just countable, my simple events are just that. You know, so it's a different, sort of a different definition, but it's consistent with this definition. And one thing you can do is you can, and I'm going to revise this. I want to change my notation slightly. I just realized there's a little typo, so you'll wait for revision of these notes. Okay, so think of this as like a micro model of the universe. Before I said omega was everything, if I knew omega star, I could know the universe. Imagine I don't want the universe. I only care about my tiny world, which is my Markov chain. And so you're constructing omega, which is just modeling this tiny planet of the Markov chain instead of the whole universe. All right? And it's just sequence, the set of sequences. So if I write omega in capital omega, it means that little omega is a sequence Okay, that's not always the case. It's a very explicit construction where each little guy here is in this countable space. And then I've got this random variable here, and I take xk of omega to be what? Just omega k. So these functions, so this is k, somebody asked, do I know these functions? Well, you can construct it so you do. This function is just taking off the kth element, all right? So it's just a way to make things concrete, which is sometimes useful. Yeah. Again, it's not essential at all. But it's sure going to make things a little bit easier today. Okay, cool. And then you can, and for example, if I wanted to look at the, if I'm given that x0 is distributed according to some mu0, some probability mass function, and I want to look at the probability that x0 equals little x0, x1 equals little x1. All right. Again, just like over there, this is going to be a probability of some event. Where it's actually given right there. It's the intersection of these guys. I'm asking that at time k I'm equal to little xk. So this event here is just the intersection of events like that. So